Great, guys. Thank you so much for having us today. I'm really excited to talk about the progress that we've made working with Velox and cuDF. I'm Greg Kimball. I'm the lead for cuDF from NVIDIA. I'm going to give some kind of an introduction and set some context, and then hand it over to Karthikeyan, who's with me today. And a few other folks on the team, Dave Everett, Bradley, Hasib, contributed really significantly to this. But really appreciate the time to get to share some of the work that we've been doing. So yeah, I'll do the first section, just talking about kind of how we think about Velox from the cuDF perspective, and then I'll hand off to the rest for Karthikeyan to walk through. So yeah, we really love Velox. This is a great community. This is a great conference. Thank you so much for having us. And we've, you know, yeah. We are just huge fans, and you know, the open source part of the community is just really important to us. It makes it so easy to get started and learn more about it and get support along the way, like the code review process, the careful CI work, really critical stuff, and it's just so great. We love it. Being a C++ execution engine, I mean, Velox is a really unique thing. There's nothing else like it out there. And part of it is just what it is, also with the pluggability and customizability. If you're looking at other engines and other data processing tools out there, they don't have the commitment to extensibility that Velox has, which made it really an interesting target for us to try to integrate GPU compute into it. Also, the good separation between execution and operators. There's a good separation of concerns. You can do operator replacement and still have it run through the same engine. That's another really powerful thing that not every engine makes easy. But really the big thing is the communities. The Spark, Gluten, Presto, C++ community, there's really nothing like it. I mean, any one of these bullets, Velox is unique, and then all together it's just it's a revolution. It's a great product. And the migration work from the Presto C++ talks in particular, you know, from Uber and Pinterest and within Meta, this is huge progress just in the last year. So, you know, congratulations to all that. One thing we really love about Velox is also the goal of being unified, not just a query engine, but also AI workflows, also streaming data, data frame processing. You know, Velox wants to do all those things, and we really resonate with that from the cuDF side. So if you aren't too aware of cuDF, I want to give a kind of quick intro. You probably know everything I said on the last slide, but maybe there's some new things here. So cuDF is also open source, CUDA C++ library. You can find us on GitHub under RAPIDS AI, and you know we've got Docker images, conda packages, pip packages you can play with. Spark Rapids jar uses cuDF. It should be easy. We want it to be easy to get started. So. libcuDF is the core here, the CUDA C++ core, the library for CUDA data frames. That's kind of what cuDF stands for. We're Arrow compatible, so it makes it really easy to do interoperability with Velox and other tools that use Arrow with the cuDF column and table data structures. And cuDF is all about really efficient single node, single GPU algorithms. And from Ori's talk, you can see how maximizing GPU utilization is critical to having a good application. So that's what we are trying to do with every function call. Whenever you call the C++ API, we're trying to use the GPUs as best we can and get you the data back with the lowest latency. So yeah, cuDF we've gotten a lot of experience working with Spark Rapids, working with cuDF pandas and polars, and trying to serve each of these different conventions and different expectations that these libraries have. So we kind of share that with Velox, where we don't want to just have one front end. We want to be able to serve any front end. And I was trying to think of a good way to talk about what's in libcuDF. So what I did here is I took the libcudf.so and just took out all the function signatures in the public API and gave them a box, and then kind of put boxes around the boxes. So each box is an API that you can call. That's a really well-tested thing, probably used in Spark Rapids. And you can see there's a big focus on I/O, doing efficient Parquet, ORC, JSON, CSV, data processing, compression, decompression on the device. We've also invested a lot in strings and list and struct support because it's great to do integers and floats quickly, but a lot of the data out there requires a lot more complexity. And then relational algebra, aggregation, sorting, stream compaction, joins, nulls handling, these are all areas that we've had to really get into the weeds with Spark Rapids and other communities. And I really appreciate the long tail discussion about UDFs. And we have a JIT module I want to highlight at the bottom here. This lets you take C++ code or send PTX directly into a libcuDF function call and apply it to your arrow data. So we have some infrastructure for this, and we really want to explore that long tail and make sure we can do that work, grow this infrastructure to support that. But yeah, today I want to talk mostly, Karthikeyan is going to talk mostly about the Velox cuDF integration here. So just to maybe say a little bit about the ecosystem where cuDF exists today. Spark Rapids is a great tool, and it kind of came up during Abhishek's talk from Google about dataproc. When he talks about Spark on GPU, he's talking about Spark Rapids under the hood, actually. So it hasn't. Spark Rapids is a pretty mature tool and a really great thing for future work with Gluten and Velox because we kind of already know what, we have a really good benchmark in what Spark Rapids is doing. If we can't run cuDF with Velox better than how Spark Rapids can run cuDF, we've got a performance opportunity, and we know we can really study that in detail with profiles. So it's going to be a really great benchmark for us to work off of is how does Spark Rapids do the same work. But yeah, Spark Rapids is a Java Scala execution engine, and one thing that Velox gives us is a native execution engine. And we have some internal projects that do that, and it's been of interest for a long time, but Velox is by far the most productive and mature tool to bring that to cuDF. So we're really, really excited about it. Yeah, and the Spark Rapids comparison is really important. And going to native, we think that we should be able to get some benefits from not having to deal with the JVM garbage collection. And looking at AI workflows, there may be some cases where Spark Rapids has a bit-for-bit Spark compatibility guarantee. And there may be some places where it costs performance to do that, and it's worth relaxing that for some workflows. And then the last thing is that having a good fallback, the CPU fallback with the Velox execution engine is right there at your fingertips, and is going to be much better than what Spark Rapids has to do today with column to row and row to column conversion. So I think this Velox cuDF has a really great performance story ahead of it. But let's talk about what it is. Go for it, Karthikeyan.
I'll be talking about the design of Velox cuDF and performance comparison. So we have most of the design of Velox cuDF extension done, and we'd like your help to make it expand it and then harden it for production. And I'll be talking about design of Velox cuDF extension and how we design the supported operators like order by, conversion, TableScan, and HashJoin. And we'll see how we can add new operators to the Velox cuDF. To put simply, Velox cuDF actually replaces the CPU operators in the Velox pipelines with GPU operators, allowing end-to-end GPU processing of query plans. So when a coordinator like Spark and Presto pushes query plans to Velox, the local planner in Velox decomposes that into individual pipelines and of operators, and drivers pick up these operators and run them on CPU. What Velox cuDF does is the driver adapter replaces those CPU operators with GPU versions before executing them. So all you have to do in your application is call register cuDF, and the cuDF adapter will take care of the rest. When you call register cuDF, it adds a driver adapter which takes care of the operator conversion. And it does a bridge translator that is used for joins, and it creates a GPU memory resource that is used for memory allocation. Let's look at order by. The order by and conversion operator support is already merged into Velox. A big thanks to Devrat Makar and Bin Cheng, who actually made this into Velox. So when CPU operator is replaced, the cuDF adapter adds conversion operator, which transfers the data from the CPU to GPU as a cuDF vector, and a GPU execution operator cuDF order by, which calls cuDF C++ APIs to run the workload on GPU. cuDF vector actually is a data structure that holds the data in the GPU. The data is held in GPU as long as the upstream and then downstream operators are executed in GPU. If there are any operators that is running on CPU, the conversion operators takes care of moving the data back to the CPU if needed. The cuDF order by operator is a non-streaming operator. So it collects all the batches, concatenates them, and then calls C++ cuDF APIs to sort them. And then it packs the results back into cuDF vector object and then passes on to the next operator. The concatenate step is needed, but it's not taking much of time for TPC-H benchmarks like scale factors less than thousands. Now, let's look at the conversion operator. So cuDF vector is derived from Velox row vector so that we give the same interface to the Velox's operators. And it has two components. One is cuDF table and a stream. Both cuDF table and Velox row vector have the same arrow compatible layout. Both of them support numeric types, string types, timestamp, duration, and dictionary types, and nested types like lists and structs. The interop APIs in both Velox and the interop APIs in cuDF allow efficient conversion, often requiring mostly only device memory copies. And the stream is managed by a stream pool. For the batch size between CPU and GPU will be different because GPU needs enough data to keep the GPU busy. So typically, the batch size will be in the range of either 100,000 rows or like a collection of like 1 GB of data. So besides converting data from the CPU to the GPU, we can start creating the batches in the GPU itself using TableScan. So TableScan can read local Parquet files using Parquet data source, and the Parquet data source it can run the decoding, the decompression, decoding, and filtering are all executed in GPU, and it adds a stream to the cuDF vector from the stream pool for each split. So when this cuDF vector is again transformed using any other operators, it uses the same stream to run on the GPU, and the same stream is again copied back to the output vector. So the stream travels with the data, so we don't have to manage stream explicitly. And this Parquet data source works with local files. Additional data sources like Iceberg or remote objects or Delta Lake, these are not scoped yet, and we would really like help from community to add them. Next is HashJoin. So Velox's hash build and then hash probe are in independent pipelines, so they communicate between them using an object called bridge. Similarly, in Velox cuDF, it uses a custom bridge. So what Velox build operator does is it collects all the batches, concatenates them, and creates a cuDF HashJoin object and stores them in the bridge. Now, hash probe can access this bridge and call cuDF APIs on the probe input batches, and then produce the output as a streaming operator. Now, besides these operators, we have aggregation operators, filter project, and local partition, and more operators that can enable us to like run the TPC-H benchmark. The expressions are supported by cuDF expressions, and this expression can be expanded with adding new libcuDF function features and functions and binary ops, and also you will be able to run transforms with using with user-defined functions. The number of drivers that is typically good enough to keep the GPU busy is around 4 to 8. So the hyperparameters that you need to configure is one is the batch size, another is the number of drivers for a single GPU. We'll see how to add new operators. To add new operators, Velox actually you need to touch only 3 functions. One is add input, another is no more input, another one is get output. Add input queues all the input batches, and no more input concatenates them if needed. For non-streaming operators like order by hash build and final aggregation, you have to concatenate them. For other operators, you can process them batch by batch. For get output, it takes the concatenated table or each batch and then calls C++ cuDF APIs on the table and the stream that is available in the cuDF vector, and then gets the results and then packs them back into cuDF vector and then passes on to the next operator. So this kind of modular designs allows easy extension of libcuDF features into Velox. And we would like developers to add more and more operators into Velox cuDF. Next, we'll see how the performance comparison with CPU. So for performance comparison, we ran TPC-H benchmarks on scale factor 100 on different systems. On the left side, on the right side, if you see, we ran Velox on a 32 drivers, with 32 drivers on a 32 core physical core system. It took around 134 seconds. And same on the same system with L4 GPU, it was able to run at 44 seconds with 2 drivers, giving a 3x speedup. And when it's run on Grace Hopper Superchip GH200, with 72 drivers, with 72 physical cores, it was able to run at 92.5 seconds. But on the same H100 GPU in the Grace Hopper system, it was able to run at 12.8 seconds, giving a 7.2x speedup. And this for the GPU, it was run with 8 drivers. Now, this is the splitter for each individual queries for the speedup. The Q4 probably has a performance issue in Velox because this abnormal speedup is due to a recent bug. But all the other queries, if you see, the speedup ranges from 10x to 3x, except a few outliers. Okay, so Insight Systems is actually a great way to visualize how GPU is utilized, and to see actually how different components of the GPU is being utilized. The main things are actually the compute, the GPU memory bandwidth, and the data transfer between CPU and GPU. So first 3 rows in this profile shows that how SMs are used, SM active, warp active, and then warp inactive. And the next 2 rows, DRAM shows that is GPU memory bandwidth. And the next 2 rows shows the bandwidth from CPU to GPU. Then the last 2 rows shows the kernel execution along with memory operations. So Velox cuDF has a very good compute utilization and also GPU memory bandwidth utilization and PCI Express bandwidth utilization. So this is a profile for query 12 on a scale factor 100 with 2 drivers on L4 GPU. All the queries start with TableScan, so it will start with copying the Parquet files from the host to the GPU. So it starts with PCI Express read, and it will wait until once the PCI Express read for the 1 thread is done, the kernels will start. But the second driver will still continue the PCI Express copy, doing a simultaneous memory copy and kernel execution. Once that's done, the second thread also will start executing the kernels. So we'll have concurrent kernel executions at the same time. So that gives us a very good GPU compute utilization. So if you see, the warp actives are mostly at the high. And memory bandwidth, it depends on the kernels that run on the GPU. So most of the kernels are actually initially will be decompression, then decoding, and then some other operators like aggregations and HashJoins. To not run out of memory for all the queries, we have to choose batch size that is like small but still big enough to keep the GPU busy. So for L4 GPU, the 1 GB batch size is good enough so that all the queries for scale factor 100 runs without out of memory. Next, we can see what is the work breakdown in the whole TPC-H benchmark on the scale factor 100. In the TPC-H benchmark, it is mostly the 85% of the time is taken by TableScan due to the high throughput joins and aggregations. If you look at the overall breakdown, the I/O part, which copies the files from the OS cache to the CPU and then to the GPU takes around 24% of the time. And the decompression of the Parquet pages in the GPU takes around 26% of the time. And the decode part, which actually does dictionary and run length encoding, decoding, and creating the Parquet, decoding the Parquet data and then creating cuDF columns takes around 35% of the time. The other operations like join aggregation run at high throughput, so it takes around, most of them takes around 5%. And there are other operations like cache and concatenation, which are very negligible, which are not even shown in the graph. If you look at individual queries, most of the queries are I/O dominated, except query 13, where the joins and aggregations is run on a very large data, so that is significant. But generally, in all the TPC-H queries, it's mostly I/O bounded. OK. So Velox cuDF is a pure C++ library, and you don't need CUDA experience to get started. So all you have to do is refer the documentation of libcuDF, and you will be able to find most of the functions that is required for GPU data processing. So in Velox public repo, we have a storyboard issue, which contains steps to how to build and how to run and then how to test Velox cuDF. And we have the first PR on the order by and then the conversion operators already merged. We have our fork with the support for other operators for running all the TPC-H benchmarks. So we'll really appreciate the community's reviews to while upstreaming these operators into Velox. The Velox cuDF is checked into Velox experimental cuDF. And this Velox cuDF brings like great performance and GPU compute to Velox. And right now, Velox cuDF is able to support TPC-H benchmarks, which only a fraction of cuDF APIs. There is a lot more functions that are available in libcuDF that can be ported to Velox. And if you are without using libcuDF, if you want to write your own kernel for certain operations, you can do so. Because the cuDF actually offers a zero-copy interop via arrow. So you'll be able to access the same data that is available in the libcuDF data structures, and you can write your own kernel to do custom operations. And to set next targets, we need community's help. We have big thanks to Bin Cheng, who actually helped with adding gluten support and then testing the order by and conversion operators on the GPU. And we expect we'll need support for spilling, for like code spilling from GPU to CPU, and exchange operators, and additional connectors for TableScan and more. That's all. Thank you so much. Thank you, Velox team. Thank you, community.